That we begin the real work next week, but today it's my pleasure to introduce Professor Ramani Duraiswami. So Ramani might be a little bit of a newcomer to people in the language technology business, people who do speech recognition, but he's been in the speech and audio business for a long time. And one of the interesting things to know about him is that although he works in speech and audio and he's in the computer science department, his PhD is actually in mechanical engineering. And you might say, what's the connection? Well, the thing is that wave propagation, 3D acoustics, those are kind of his passion. And in fact, he has a actually, do you still have the company or you sold it?
I sold it.
Okay, so the company has been bought. It's called VisiSonic, I think. And they do 3D acoustics, both capturing audio and rendering 3D audio. And he's been in that space for a while. And of course, he also does algorithms and the usual stuff that all computer science professors do. You can read more about his stuff on the web. And very recently, he got into this business of thinking about audio understanding more generally. And today, he's going to tell us about the plans for his team to do. We started calling it AUGI very recently, Audio General Intelligence. So, Ramani, all yours.
Thank you.
And Katya, as usual, questions, use the mic.
So, it's a tremendous privilege for all of us to be spending 6 weeks or more working together. And in general, research happens, at least so far, it happens when people talk to each other. Maybe in the near future, it will happen when you talk to an agent, but who knows that. But for now, we have a tremendous opportunity to interact and advance research in auditory general intelligence, if on my topic, but on others' topics, on many other things simultaneously. So I want this to be interactive, so please interrupt with any questions that might occur to you along the way. Yep. So this JSALT is named after Frederick Jelinek. He was a professor at Hopkins and sort of interesting. I met him personally a couple of times when I visited Hopkins, but I didn't know him. I was perhaps visiting Hinek, and he might have introduced me to Frederick. And so like I said, it's a unique opportunity to go deep. And perhaps you can also consume other Jelinek stuff, which is this plum brandy, which is the drink, and it's also, so it must be a relatively common Czech last name. So today we are going to have the usual format. So a couple of lectures in the morning, and then followed by tutorial, and please ask questions again. So obviously I'll be here for the 6 weeks. It's too loud. Yes, thank you. I'll be here for the 6 weeks, and it's sort of good to know, as Sanjeev already introduced, it's good to know what my background is, because we might be talking about what we're doing in our project, but you might also have questions about other things. So I just wanted to give you a quick personal introduction for myself. So as I did a BTech in mechanical engineering long ago from India. Then I did a PhD from Johns Hopkins in mechanical engineering and applied math. I've been a professor at UMD since '98. I worked on many things, but I sort of, one of the interesting experiences in my life was launching a startup. So we developed 3D spatial audio rendering and personalization tech. So that experience was interesting, and my spatial audio stuff is in the Oculus headsets. So if any of you sort of experienced the 3D audio in an Oculus headset, that came out of work my students did. As I said, I worked on mechanical engineering, applied math, so I have background in modeling wave propagation. I also worked on computer vision, human audition, fast algorithms, parallel computing, and statistics. But because I was busy, I was at the startup and working on this stuff, what that meant is I missed the first wave of deep learning, recent wave of deep learning. And so all this CNN business I didn't work on, or in the context of audio, I didn't work on LSTMs and stuff like that. So maybe that was a blessing. So when I exited the company in 2023 and came back, the students now wanted to not necessarily work on the stuff I was interested in. They were more interested in working on deep learning, so which was happening then. But fortunately, deep learning also had changed. The transformer architecture had come, all this LSTM business and CNNs, etc., were no longer as, a la mode. And so I could look at transformers and audio and sort of join at the same level as everyone else, again, into the deep learning research. So in general, my background in research is sort of vision, audition, scientific computing, and machine learning. More recently, so here I'm going to be talking about large audio language models mostly at this workshop, but I've also worked on many other things which might be of interest to some of you. In particular, one big theme of my current research is how do I do research which was sort of relevant 20, 30, 40 years ago, which was based upon modeling things, but fit it into a deep learning context. And so that is, half my students work on this area, which is deep learning that is informed by forward modeling. And we sort of try to combine that into things like generative models, operator learning, and physics-informed neural networks. And I also worked a lot on spatial audio and so on, which I already mentioned. So before I jump ahead into today's conversation, today's talk, I'm going to just show off a couple of things we did in the past. We built a camera for sound. So you might ask what that is. So if you look at an image, every pixel in that image represents the energy of light coming from a particular direction to the sensor plane of that image. So what we wanted to do was to create something equivalent, a display device for sound, which was a bit like that. And we created microphone arrays, which would be able to record scenes and create visual images, which represented the energy of sound. So what does that? So here is my student Adam. He developed this as part of his thesis work. He's snapping his fingers. As he snaps his fingers, you see that image light up. And essentially, the top is the audio image that we did using microphone array processing. And that same image is overlaid on the video below. Another thing we used this for was to sort of look at concert hall acoustics. So here we create a single sound from the stage of a concert hall, and you can see the reverberation going through the concert hall, and you can see all the reflections as it happens. And this was quite interesting, and actually this back effect, most concert halls will have a curved back because you don't want a very bad reflection from the back. We showed this sort of spread reflection due to a curve back to the original designer of this concert hall. And he said, I always designed these concert halls to achieve this effect, but I'd never seen it demoed. And this person, he was quite happy in it. So this device continues to be sold into automotive and into architectural acoustics. And we also developed 3D audio for games and virtual reality. This is, for this demo, you have to hear it over headphones. But I'm just going to skip ahead. But as you move around in a game or a space, you get 3D audio according to where you are in the space. And several games have been shipped with this stuff. Okay? So as I mentioned, now I'm into this machine learning phase of my career. I missed the first wave of deep learning. So after I returned to the university, I'm trying to sort of do things which I can use my skills to do deep learning. And differentiability and sort of tweaking transformers and so on, but also looking at audio processing in foundational large audio language models. Okay, so 1 second. There is some animation, but which is sort of going to be missed. So because I added this last image in a second, but that goes fine. So the topic is going to be led by 4 of us, me, Santosh, Alicia, and Paola. Paola hasn't yet come, but she should be joining us within a week or 2. But one big change I realize in research is this business with large language models is very experimental, and it requires intense work on the part of students, and they essentially lead the work. And that is also the case in my group. And the 3 students who have been leading the work over the last couple of years in my group, Shreyan Ghosh, Sonal, and Sakshi, and Lasha is joining our group. And they have been tremendously sort of productive. And these are all sort of conference papers in the last 2 years which have come out of the group. And these are all accepted papers. These are not just sort of, and there are several other papers which are sort of in the process of being created. So obviously, this requires a tremendous amount of dedicated work and continuous work. And we are now in this phase where science itself is changing. And essentially, you are achieving extremely impressive results compared to what we were able to achieve in the past. And in some sense, while the rest of the world is a little bit scared about where AI and LLMs are going to lead us, you folks are going to be in the sort of forefront of this huge inflection point in where things are going. GPT just came out, ChatGPT just came out 2.5 years ago. And there have been, every month, there has been new innovations, new things going on with these large language models. Of course, they started with language, but now these models are being adapted to include interactions in the real world, adapted to include interactions with vision, with audio, which is what we are working on, with robotics, with actual agents in the world. And there is, in some way, you're sort of, you have many, many opportunities to affect what's going to happen in the future. Everything is working, but everything is sort of also in its beginning. There are many, many opportunities to improve things. And in some way it's scary, but also in some way it's a tremendous opportunity. Right? And so this is sort of the first pause in my presentation. So I just wanted to get perhaps an opinion in the audience of what you feel about doing research in this era. Does anybody have any thoughts or opinions about the fact that you're doing research when I went to school, when I started doing my PhD, we studied stuff which was 100 years old and didn't change too much in fluid mechanics, right? And on the other hand here, you guys are sort of doing research in an era where things change from the beginning of the year to the end of the year tremendously. So any thoughts on that?
My thought is that I'm grateful to be here.
Yeah.
My thought is that I'm grateful to be here because I am eager to do research in this new and exciting developing field of artificial intelligence. After all, artificial intelligence is my lifetime passion, and I really want to see, how far we can achieve this summer, but also I want to see how I can learn to be an AI scientist and grow my skills. I really just want to see where this field will take us because I know that AI will be will be greatly helpful, will greatly beneficial to humanity in the future.
Yeah. Any other thoughts? Yeah.
I think I'm just going to continue to be surprised by the pace that it moves at. Like, I think even just within the last 2 years, some of the things that have happened, I would have expected to take like 10 years. And I think a lot of the stuff as well, we're doing so many things that like, even now we're not completely understanding, and there are whole fields of just trying to understand it better. And I think that'll be the biggest stuff that'll happen, but I think I'm just completely always surprised just how fast things move.
Anybody else?
Yeah, I agree, and I think the most exciting thing here is what we are doing with machine learning, artificial intelligence is just taking the information in the real world and approximating some stuff. And now we are able to take into account nearly all the information that we can get from data. We have multimodality, which we are converging towards. We are jointly training things. So we are getting we're trying to get every bit of information out of our data. And it's moving very fast in this manner, as Finn said. So I think that is very exciting. We are not leaving anything behind.
So that is certainly the case. Of course, it's also a little bit scary. One of the fears is, as we sort of keep going along, and it's not a fear necessarily, maybe it's just a fear that we'll become less relevant as humans. But on the other hand, for humanity, it might be a good thing, who knows?
Now, I was going to ask some of the PhD students if, okay, Dominic.
Yeah.
Because I have a fear for my own students, which I'll tell you later.
Yeah.
I mean, in this era where everything is just developing so quickly, it's really, really cool to see that everything is happening and you can witness so many groundbreaking changes in the field. But also on the other hand, I think that like researchers are currently just striving to get the best numbers possible without actually thinking what they're doing. So I think this is like the opposite side of the research. Like everything is happening so fast, but at the same time, people are not thinking about what they're doing. They're just trying to beat the benchmarks and numbers.
100%, yeah.
So yeah, I think this is the drawback of the entire like fast.
So I think that's both a benefit and a curse. One of the sort of big mind changes I see is in the past, we would sort of propose something because it was, we thought there was some beauty to it, but we didn't really care too much how much error there was in the thing. Now the way of doing research is to drive down errors. Of course, that leads to the problem you said, but on the other hand, that is a fundamental change in the way research is done. It is very sort of error-driven kind of a thing. And we also have new ideas of how to measure errors. We measure different kinds of errors. We do sort of different kinds of optimality and so on. Any other thoughts before I move to the next thing?
It's definitely scary. There's a funny saying that there's so many ML researchers that when you get an idea, there will be 3-4 people in the world who will get the same idea.
Yeah,
And then it's just a race to the clock on who beats who, and then, so it's a little intimidating and you can't relax too much, and then you have to work more than what you used to do before.
Yeah, it's, so in some way, what this has led to is, older faculty like myself, we are used to a certain pace of doing research. On the other hand, the pace of doing research students have realized is quite different. Over the course of their PhD, if they have to sort of get these papers and so on, they have to work not only get the idea, but they have to work on execution much faster, or they have to get a fundamental new idea, which of course still has a role in doing stuff. Okay, so as I was saying, so there are sort of two components to these large language models as they're implemented. The first is this classical machine learning based training, where you train on all the data available using this transformer architecture and predict what the next token is going to be. So predict what the next thing is going to be in completing a sentence in a sort of autoregressive fashion. But then this second piece, which is what sort of aligns it with perhaps the way humans think with all the data that they have, is this agentic thinking, which was introduced to the world by ChatGPT, was essentially allowing you to question the model and have it give you answers in some interesting way. And it was released only end of November but in 2022, and we are less than 3 years into the future, and it's basically taken over the world, and now they're sort of getting into all sorts of different modalities and so on. The two countries are currently dominating the top current models, the US and China, and all the research is, one big change is that when I was doing my PhD, research was mostly funded by the government, and now the center of mass for doing this kind of research has moved to companies. All these biggest models are run by big companies. So you have the usual suspects, Google, Meta, and Alibaba in China now, and there's some sort of startups, Anthropic, DeepSeek, and XAI. And it's academics contribute, but it is now an experimental science which requires lots and lots of data and lots of compute. Right? And so this has required a reassessment on the part of academia as to how one collaborates with industry and how one can potentially expose your students to the latest research by letting them, in a sense, also work with the industry. And that is a big sort of cultural shift, at least for me as well. So this is the sociological part of my talk as I move on to the more technical aspects. Okay. Just as a matter of advice, I encourage all of you who have the opportunity to develop collaborations with industry if and when you can. Just because the type of research that you'll be exposed to is going to be quite different from the type of research that you will experience at the university. And you'll be richer for that, yeah. Okay, so now let's sort of take a step back and think a little bit about what goes on. And you've been, I attended the lectures yesterday, and some of this material was there in that lecture as well. So if we are sort of looking at this, training these large language models, one can sort of divide it into 5 different things. So there is an architecture that one proposes. The transformer architecture is the one most of us sort of work with, though there are more interesting state space models and so on which people are exploring but haven't yet been able to make a big success of yet, even though it's sort of very promising. So into this architecture, you feed in data. The architecture has a bunch of parameters, perhaps weights, which you learn by trying to minimize the error on that data. And you minimize that error on that data using training algorithms and loss. And some definition of a loss. And most of our academic work is focused on these 2 aspects. On the other hand, an interesting thing which has come up is this training architecture, which is today's fundamental thing, the transformer architecture. It seems to continue to learn the more data you feed in. The more data you feed in, the more it learns. And these kind of scaling laws, which people have come up with, which show the more compute you throw at it, the more data you throw at it, the more it learns, kind of. And it seems to be like this beast which has an unsatiable appetite, right? So, how do you get that data? And there are many issues with that data. Of course, as humans, we collect data by our life experiences, by hearing things, by seeing things, perhaps tasting and smelling, and touch and all that, though they're not yet large models for those, but perhaps there will be at some point soon. And then, of course, you have to evaluate things. When you evaluate things, so there is one thing associated with error minimization, and there is another thing associated with, even if your system achieves low error on your training data, what does it mean in practice? How does it function actually? And then there's lots of systems things. NVIDIA has become the most valuable company in the world because essentially they cracked the problem of how to build usable systems. No other company has been able to really create software and systems that can be trained as easily. Right? And these last three things need massive engineering resources. Okay? Any perspectives on any of this so far? Any agreements, disagreements, anything? No. Okay, let's. So let me stop for a second because I'm going a little slower than I wanted. So let me just skip a slide and move on. So these large language models, they're just trained on language, they're just trained on text. Of course, what has happened is all the writings of humanity have become converted into digitally accessible stuff. And these large language models, they take months to train. And this is just talking about the pre-training part, where the transformer architecture is trained. And it's trained on all the internet. It's trained on billions and billions of pieces of tokens. This is a totally different scale. And the internet has, and the data is often very, very dirty. The internet has so many pages which are useless. I myself must have created 20 web pages which I started and never finished. And all those are there, sitting, and that is all being, sucked into these things by common crawl. And then all the text is extracted. There are many, many copies of, the same web page. There is very high quality data, perhaps from Wikipedia or other sources, or from textbooks, and so on. But there's also a whole bunch of junk. And somehow you have to train on all of this. And the data to the algorithm doesn't, come as clean text. It comes with lots of hypertext embedding, etc. It has the HTML tags. It has all this weird URL stuff, etc. But somehow it is lots of engineering. They've figured out, and each piece of this cleaning, filtering, etc., has had research done on it. Why am I mentioning this? Some of this research is lacking in the audio domain. We do not have such, filtering type stuff yet in the audio domain, and there are tremendous opportunities to sort of work on that. Yeah. And this is data on on how sort of creating, how I mentioned, the more data you feed, the better your algorithm performs. And the language people have figured out how to create more data, how to create synthetic data, how to process data well and efficiently. And all of this stuff is being done by companies, as I mentioned. So there's lots of secrecy. There's lots of things which are hidden for competitive reasons and so on. And there is also tremendous sensitivity because humans were the ones who created the data. It was their life's work. They consider it valuable and so forth. And there are copyright rules which governed it. But on the other hand, if you have to train these models, there are concepts of licensing the data and using it. And there are concepts of sort of fair use, etc., which people sometimes claim, academics perhaps more justifiably than others. But all of this is, because of the scaling, the more clean data that you fit into your model, the better it's going to perform. And we need to figure out where to get that data. There are sort of academic data sets which are relatively small, but there are much, much larger data sets. And the data is measured, size can be sort of measured in tokens. These are all language data sets. I just want to sort of show you this number. 15 trillion tokens, 13 trillion tokens. And what this also tells us is really LLMs are all about language so far. Even the large audio language models, the large visual language models. Because the number of tokens these large audio language models are going to be trained on, the audio tokens, is going to be much, much, much smaller than the trillions of tokens that you have to train language. So really, if you sort of imagine humans and animals, our primary tokens are visual and auditory. And language is a higher level sort of abstraction that we created. On the other hand, these large language models are sort of inverted in some sense. You have the language as the primary thing. All the tokens are coming in from the language, which is some sort of a distilled version of what's going on in the real world. And we are tacking on audio and vision on top of this language. And this creates, if you will, a confusion sometimes on the part of older researchers who were dealing with language as a primary thing, not language, as dealing with the signal as a primary thing before. And now you have to sort of defer to language first and then come back to your signal of interest. Yeah, so I'm going to just jump this. So to train Llama 3, 400 billion, it cost about $85 million and took 6 months. Which is why all this stuff is done at companies, right? You need people to invest, and you need people who are trying to figure out how to get that return on investment. So this slide is taken from a recent OpenAI employee and a Stanford PhD, Jan Dubois. He has a couple of wonderful presentations on YouTube. You should look it up. And there are some interesting things here. To train every parameter in the model, this 400 billion parameters, they had 40 tokens per parameter. So which is, 40 times 400 billion, 16 trillion, whatever that number is, yeah. And the next model after this will be 10 times more flops. There's lots of carbon emitted, but probably it's fewer than the amount of carbon emitted by you guys coming to this workshop. But still, there's sort of just a... So the next thing you need is you have to evaluate the large language models. And industry does a lot of good evaluation, but there are also tremendous opportunities for academia because this is, what, in some sense, humans know what is good and bad, and we can somehow use that thing. And there are many interesting questions about this. These are the benchmarks that are used for LLMs. I'm going to just skip through these. We have to develop similar benchmarks for audio in whatever we are going to be doing in our project. And in particular, much of the work we are going to do in our project, there are going to be two fundamental pieces to this project. One is improving the architecture of the language models. That's what we'll go to second in our project. But the first piece in our project is going to be related to how do you build a large audio evaluation benchmark that you can test many different audio models on. And much of the work is inspired by this paper called MMLU, which is sort of an older version and then a newer version of MMLU in the era of large language models, which is trained on many pieces of data. The many areas you ask the language model questions, and you give it scores on each of the different areas, and then you get an aggregate score. And these different language models, they do somewhat poorly in all of these. And then, of course, then it becomes a game. You mentioned that game, right? Because each time someone creates a test, people try to pass that test. And sometimes they build a question bank and they learn the answers, and that test becomes useless. And that happens with large language models as well. And so it's a constant arms race. How do you build this question, and how do you build this answer, and so on. So, and quite often it happens in real world that the question which is set in the exam is a bad question. It's a wrong question. This happens more when you're setting so many questions as we do to language models. So there is sort of inconsistencies in the way the questions were set, which leads to statistical issues in the answers. And there is this train and test contamination. If you publish a test, sometimes the next version of the model is going to be trained on that test, if you will. Okay. So let's come to the next big issue. We want to advance research. And one of the big issues is lots of things are hidden about how these large language models were created. There has been, the saving grace for academia has been Llama 3.1, which the Llama series of models, which have open weights and somewhat open source code. But every other model, all you can see is what they actually do. So there are three elements to this, like I mentioned. What is the source code for training and for post-training, pre-training and post-training? What was the architecture and the weights? So that's one level down. And an independent thing is what data was the system trained on. And then the fourth thing you can do is you can evaluate it separately and check how it performs. So if you sort of look on this column, training data, all of them are closed. Of course, one reason all of them are closed is some of them are afraid that they might get sued, that they violated copyright and so on. So none of them want to show their training data. Source code is mostly closed. Even when it's open, it's only partially open. There is sort of lots of secret sauce there. And weights, for many of them, it's closed. But for some, the weights are open. And for these, we can do various things which are, knowing the architecture, we can do simple things like fine-tuning these to get, add capabilities to these architectures. Okay, yeah.
What do you think about the safety considerations to making models open source, both geopolitically and in terms of AI safety and misuse? What are your thoughts?
Yeah, so the question was, what do I think about safety considerations, about open source and open weights and open data and so forth, both from various aspects, both geopolitical and perhaps other methods, other safety issues that one might consider. So, in some sense, my generation did not grow up thinking about safety because we didn't, even though sort of nuclear things were sort of an existential thing for people from the 40s to the maybe 60s and so on. I grew up after that. And so we didn't have this feeling necessarily that, things are going to fall apart kind of a thing. Perhaps the next generation had that fear, I don't know. So here, in some sense, I grew up with a feeling that openness is the answer, which is that the more you do things in an open fashion that allows people who are concerned about safety to also deal with the consequences. You know what is going to happen. On the other hand, that might be sort of a little self-serving in the sense that because I want to do more research, so I hold a philosophical position which helps me in that fashion. So that might not be the correct answer. I have to sort of examine my own motivations to think in that fashion. I do feel sometimes, the word safety is used a little bit as a crutch to create fear, uncertainty, and doubt. Sometimes those safety feelings are a little bit overblown, but on the other hand, there is. I would like to get your who has the microphone, perhaps? Yeah. Your thoughts too, because you asked the question, so I want to get your.
So I follow Jan LeCun, and he's also very pro open source, and I think that's why Llama and
I also follow him. Yes.
But I'm also pretty involved in the AI safety scene, and I think some of the fears are that on the one hand, having closed source models is bad for safety because you don't know what companies are doing, and you can't check if their models are good. But on the other hand, these models are so powerful, and if put in the hands of bad people, they can bypass the safety measures that the models have and get access to certain information or use it for misuse. And also, I think we're in a little bit of a race with other countries. And so I think there are some motivations to for some countries to want to be the first, which I think is wrong to have that race in the first place. But, so yeah, I'm torn. I have mixed feelings, which is why I wanted to see if you could justify your.
I've only thought a little bit about this. I haven't, thought deeply. What I will say is many of these problems exist with or without AI. AI is, of course, trained on the rantings of various humans, which is worse on the internet than potentially, what's, otherwise. And it has lots of biases. And the same humans who, might sort of put down populations or have biases, do genocide, etc., have access to this technology. But I think at the same time, potentially people who work against them also would have access to this technology. This is a version of the argument which I don't like as far as guns are concerned, where people say that, guns don't kill, it's people who kill, but that's not true in the sense that because, if you give, you can do much more damage. So I do not have a great answer. Sanjeev?
I was going to say, we don't want to derail your lecture, but this is a very interesting topic, so I'll just make a comment anyway, which is that there are really two sides of the concerns with modern AI, and the more, organized one, if you want to compare with nuclear weapons, right? What could a state do with this kind of technology? You could do mass repression of people, you could build armies of killer droids, and all that. And I think that kind of risk needs to be managed in one way, like people managed nuclear weapons in the 60s. But then there's the other kind, which I compare, for example, with research in virology, gain of function research and how to change viruses, right? A lot of medical applications. But do you really want that technology out there? Because one crazy person can build a virus that will eliminate millions of people. So I think the second risk is of that kind, where with these AI tools, individuals can do a lot of damage. And there it's comparable to your guns don't kill people contradiction. Yes, in general, guns don't kill people kill people. But if you start giving people automatic weapons that can fire 300 rounds a minute, it's very different from giving them a pistol which fires 1 per second or something. And you are empowering people to do more damage. So I don't know, we could debate this all day, but anyway, if anybody has any strong feelings, you can take a minute, but otherwise we'll let Ramani move on.
Yeah.
I do like the comparison, like the guns and automatic weapon comparison, but it's obvious, AI, I think, can be used for a lot of positive things. Guns, on the other hand, I don't really see the,
Yeah. Great. Okay, let's now move from the philosophy. Oh, sorry, was there someone else? No. Okay. So what I'm going to do next is, I'm not going to play many of the audios. I'm just going to jump ahead to a few things. We hear, we see things, we locate things, we communicate with sound.
In his hand, he had that acting.
Yeah, and there's also lots of non-verbal audio, which sneeze, cough, etc., things clapping, and so there's lots of research going on in building large audio language models. So there is a new element to this list. So in terms of open source models, there's a bunch of audio models. So we are lucky to have the authors of Salmon, LTU, Gamma, Audio Flamingo 2, and Audio Flamingo 3 involved in our workshop. So these are the open source models. There are a bunch of proprietary models, and then there are the Quen family of models, which are open access, which allow you to sort of look at the weights and play around. And there's also Audio Flamingo 3, which is open, completely open source, open data. We have both the architecture and the data available. So this is the large language models, and part of our research project is going to be looking at these open source models, Audio Flamingo 2 and Audio Flamingo 3, and proposing improvements to how they deal with training of the model, and how to propose new algorithms to train and new data sets to train them on to get better versions of the model. The second part of our project, and Santosh is going to talk about in the second part of this tutorial a little bit about how we might improve the architecture of these models in there. The second part of the model is evaluating the state of the art. And on this, we are going to be basing our work on this paper MMAU that we published earlier in the year, which is a benchmark for evaluating audio, So this is essentially, we have put together a bunch of human and LLM created question-answer pairs, which cover 3 domains: speech, music, and sound. We try to, in these question-answer pairs, look at things like how well sounds are understood, how well world knowledge is sort of captured, and much of this will come from the LLM, which underlies this stuff, and reasoning. So much, and test this system, which is this large audio language model. But remember that this system is built on top of an LLM, and much of this testing will test the underlying LLM. But of course, we do want to move in a direction to get more audio in, rather than just sort of looking at things. And so there are various things already in MMAU. And remember what I told you. As soon as you publish a test, people sort of train on that test. So when we are going to be creating a new set of tests here, we will have to devise new question-answer pairs and new skills to test these large audio language models in. And one of the things is we are relatively early stage of audio research, of large audio language model research. So LLMs developed many things 2 years ago. That stuff percolated down to vision 1 year ago, and it's only now coming into the audio stuff. So in some sense, there are far fewer numbers of people working on audio than are on vision, and there are many, many more people working on language. So in many ways, we have a tremendous opportunity to piggyback on their work. Of course, we have to adapt things, and we have to do it. We cannot blindly copy, but at the same time, we can copy. And so that requires, so there's too much stuff published now, and much of it is junk, but we have to sort of glean the best nuggets of ideas from that literature and bring it into what we are doing in building these tests. So here are some examples which are, so I'll play examples later in the end. So the big thing is when we publish this thing, the best performing model was at sort of 65%, whereas in LLM tests and in vision tests, many of these models perform in the 90% range. So the audio models, even the expensive ones trained by these big companies, don't do well on this MMAU thing that we have. What we want to do is to build an even tougher test with more questions here. And this is really a place where this workshop can tremendously advance the state of the art, because many of you have backgrounds in audio. All of you are humans who sort of use audio throughout their lives and have a certain expectation about audio understanding, which we need to capture into question-answer pairs, which we'll be doing. And in terms of things like music, people really, all these examples, all these language models really do very poorly. And that is going to be another theme we are going to focus on. We are building huge database, trying to build a huge database with music because, and multicultural music at that, because this is an existing huge skill gap in the current state of the art in language model, in large audio language models performance. There's lots of errors in actually perceiving what's happening in the actual content. So this reflects perhaps that the audio tokenizer is performing quite poorly and is losing information about what's going on in the incoming data. But then there are other kinds of errors as well. Some of them are related to the performance in the language model. So some of this error has been addressed in Audio Flamingo 3, which was not part of the, yeah. Yeah. So the way the things work is these are all multiple choice answers. And there are lots of questions, and Santosh and I, we have been having robust discussions about how significant some of these errors are themselves. Are the errors themselves, is there a flaw in the methodology of measuring the errors? But that being said, there are two ways of evaluating how things do error-wise. So the simple way for an academic test is to look at multiple choice answers. And you have, let's say, 4 answers, and you have one as the correct answer. And you ask the audio language model, what is the answer to this question? And when you do that, it makes an error, and you sort of flag it as an error. So at chance, it would work at 25%, if you will, right? So you look at how different it is from chance, and you do that. The other way of measuring error is to feed it to a higher level higher level language model, and check if that output is if that language model thinks that the answer is good or not. And in this case, you sort of have an API key to this large language model. You take the output of your thing, feed it to it, and you ask via prompts how well it does. I explained the methodology. I didn't show you examples of the answer, but just to sort of give you the background. Yeah. Yeah. You're getting a workout.
So these are combined audio language models, and audio and language are not that separate. But with all this measurement, like it's very intuitive, like a question answering. But these all have the language, the text component.
Yes.
Do you think it is possible to isolate the audio component and do these types of generalized benchmarks only on audio?
It's an open question. Like I sort of emphasized a couple of times, we are piggybacking on language. And much of our learning is sort of based upon fine-tuning the language model. We are not fully training the model with both audio and language together at the same time.
Sorry. Yeah. Do you think these errors can be mitigated using like more architectural work, improving the...
Absolutely.
Oh, okay. Or do you think it is because we don't have this type of data self-supervised or supervised for audio?
I think all of the above in some way, because we are in early stages of all this work. So there is, of course, more data, better questions, better answers, better question-answer pairs to train on, and better architectures. All of the above are sort of called for. And that is why this is a nice workshop at a nice juncture, because we have the method, the means to do it, kind of.
Yeah. No, Ramani, my question was more basic. What I was trying to figure out is, when you call something a perceptual error, what does it mean? So, like, if the question was, what instrument is this? And you hear some audio.
Yeah.
And the answer comes out to be wrong. Is it because of a knowledge error, meaning the thing doesn't even know what that instrument sounds like? Or is it a how do you distinguish between, what was the definition of an error type?
So usually a perceptual error is, it might say there is no music in the thing, when there is obviously there is some music in that thing. That kind of an error.
So what would be like a knowledge error, for example?
A knowledge error is, if you asked it about a particular kind of composer and it gave you the wrong composer or something else. It lacks the knowledge about that underlying language. The LLM perhaps lacks that knowledge.
And is this part of the paper?
It's part of the
to understand this. I still don't get it.
The examples, I can sort of jump in, but I have only 10 minutes.
Okay, all right, thanks.
Yeah. So now I'll come to playing a few demos. So here, these demos are based on Audio Flamingo 3.
Oh, I must be in the wrong class.
Oh, no, you're in the right place.
Did I get the time wrong?
No, it's just you and me.
So this is some demos from Audio Flamingo 3. And the question you ask is, how many students are in the class? And the answers are 3, 2, 5, and 1. And the output is, the answer, if you sort of listen to the audio again, the kid says it's just you and me, right? Did you? Okay. And the answer is just you and me, so the presence of a teacher and the sound of a door suggest a classroom setting. So the most plausible answer is 1, and this is what Audio Flamingo 3 says. This is... So this is, some guy singing along, too loud again, clipping. Yeah. So some guy singing along, and then the question is, generate a caption describing the scene, considering spoken content, background sounds, and music. And Audio Flamingo 3 answers, a man is driving, singing a sad song. Nothing really matters to himself along to the radio. Okay? One idea which we often encounter is essentially ASR has made tremendous advances. So the question might be, can we just take the input, use ASR on it, and then let the LLM handle all the queries? And it turns out that this sort of a cascaded system which use the ASR transcript and the caption and then feed that into an LLM, that doesn't answer the question that we asked. But in some situations, this is a valid approach, but it's sort of something worth comparing with. So here is another. So this is a saxophone. Perhaps if I played it, that's how it would. No, this is a saxophone being played, but actually it was being played intentionally to try to create the sound of a wailing dog. And the model seems to understand that. I don't know how it figured that out. So the saxophone is played in a way that resembles a dog howling kind of a thing. And then here is some music. Oh, sorry.
Tô cansado, cuspo fogo pra te esquecer.
And the question is, it feels peaceful and introspective. Why is that so? And the thing says that it's because it's gentle instrumentation, slow and steady tempo. So now let's sort of come to something which is new and which is sort of a frontier thing in this thing, which is how do you compare audio? So you feed the model 2 different audios and ask it for some question comparing the 2 pieces of audio. So the first piece we feed it is that same audio piece that I just played. Hold on. Come on. So anyway, it was basically taking one piece of music and another piece of music and asking the thing to transform how would we transform one track to the other. So the audio language model gives an answer saying you can start by increasing the tempo, introduce drums, and so on, and which sort of seems a reasonable thing. And the other, so most of the previous large audio language models output in text. So the next thing to next frontier is how do we make it output in voice or music together. And that is really a frontier problem. And many recent VC investments have been sort of focused at improving the quality of chat. And people like Andrew Ng and Sergey Brin and all have said that this is the frontier problem currently in what they're trying to do, getting a completely chat-to-chat kind of a thing. So Audio Flamingo 3 has some rudimentary voice-to-voice stuff. There is a whole demo website associated with Audio Flamingo 3. You can go and check it. And we also are going to be releasing a place where you can upload your own audio and play around with it and questions. But of course, by the end of this workshop, we'll have a better thing where we will actually answer more questions and so on. Yeah. So let me jump ahead to my last couple of slides. I'm already a few minutes over. So one of the big problems in audio has been, because audio has been tacked on top of large language models, is that initially most of these things only dealt with 30 seconds and a minute-long clips of audio. With this Audio Flamingo 3, we have gone up to about 10 minutes. But on the other hand, people want diarization and summarization and questioning and needle in the haystack kind of problems for audio pieces which are 1 hour long and so on. And that remains, so for example, you might have a conversation between two people, and that conversation starts off, everyone is positive, but then by the end of the conversation, the second person is sad for some reason. Understanding that change of dynamics would be sort of a skill that we would want to teach these models. And that has also lots of architecture issues. We want to also add video to the audio so that now you have a truly multimodal kind of a thing. Then you want to do reasoning. And you sort of, for example, here you might have a ball being hit and bounced, and this you might sort of, from the audio itself, know when the point got over and so on. Then what kind of music is being played, those kinds of questions. We need, again, question-answer pairs. And then you need chat. You sort of, you need to be able to ask multiple questions following on, building on top of the other, or one on top of the other about the audio, and have it. So there's improvements that I mentioned that, to address this errors associated with perception, much of the errors came due to the encoder. We worked on improving the whisper encoder to make that better. And the current training architecture is complex, but there are many opportunities to improve it. And one thing I will remark is the training is based upon various ways of doing fine-tuning, but the language models and the vision people have moved to something called preference optimization. And we, in the audio community, haven't yet achieved success with preference optimization. And So the question remains, why haven't our attempts at preference optimization yielded the kind of results that could have been there? And so that is something one of my students at Maryland is looking at, but this is something certainly we would also want to look at in our thing. So we have lots of
got you a present.
Lack of data. We don't have reasoning-centric data. We don't have long audio processing data. Open source data is relatively small. The audio community usually dealt with clean data. On the other hand, data that you record from YouTube, et cetera, is pretty bad. And the audio encoders, for example, only achieve 50% on audio set. On the other hand, ImageNet, people are able to achieve 95%. And then there are lots of linguistic variations. And these communities, speech, sounds, and music, sort of have their own sub-communities and don't necessarily talk to each other. So these kinds of things. Benchmarks need to be improved. So essentially, this is what we are going to be dealing with here. And I think I'm going to wrap it up here because I've sort of ran on for a bit. But hopefully, I gave you a flavor of what we want to achieve in this workshop. And I also gave you a flavor, I'll be around, come and talk. Let's all interact and so forth. Thank you.
Any questions before we take a break? Questions?
Yeah.
Yeah, hold on.
If you would like us to do one thing to improve LLMs of this workshop, what would it be?
Give us data and questions about that data that you think would be interesting for an audio language model to be able to answer.
Okay.
And that will sort of constructively allow us to improve both the data sets and the evaluation in a way. And if we fail in answering your question, then also it might give us an idea of what architectural improvements may need to be done.
All right, thank you.
Do we have a measure of how these models use audio and language separately? Like, for example, in the question where it's had, like, you can use, like, drums and stuff, how much of it is because it actually understood the audio, and how much of it is because we gave it the prompt and then the language model has, like, that information that learned somewhere from the language data?
So those are all frontier research questions. We are trying to tease those things apart, but there are various ways of doing the test. First, you only sort of question on the audio, then you only question. But as you get more and more into reasoning, I think it will rely more and more on the LLM.
All right, Ramani, how much, 10 minutes?
It's 10:30 now,
Yeah.
so I think...
So let's do a 10-minute break, get back at 10:40, and Santosh will continue?
Yeah.
Or? Okay, all right. Okay, 10-minute break. Let's start the second part of the morning lectures. This will be given by Santosh Kesiraju. Santosh is a senior researcher here in Brno in the speech group, but his association with the workshops actually goes much longer. He was a visiting student at Hopkins, 2017 or something like that, 2018, 16, yeah. He worked on unit discovery, like, automatic discovery of structure in language, but then he did his PhD from IIIT Hyderabad. But somewhere in that journey, he came through Brno, found himself a wife, and decided to stay. So, Santosh, it's yours.
Thank you very much, Sanjeev. Okay, so I believe this will be the last lecture of the summer school. So it's going to be easy for me because I assume you already know all the basics. And I will directly jump into some very few applications that we were working on. And I will try to share our findings and some of the open questions. Okay, so again, I'm going to talk about aligning foundation models for speech and language applications. And I will briefly tell you what I mean by foundation models are aligning and what are the applications that will come. So again, when I say foundation models, at least for the sake of this talk, these are large language models, are large speech or audio models that were trained in unsupervised or self-supervised fashion or semi-supervised fashion on lots of data. Not particularly for a specific task, but for some generic task as a pre-training objective. And then I will talk about aligning foundation models and two applications that require or that this alignment it will be used, and some kind of conclusions or limitations or takeaway messages on what to expect from this. So the reason why we call it, or I see as foundation models, is when they are pre-trained on lots of data, they kind of acquire some kind of abilities to do certain tasks. I think in last week you have seen some lecture from Ondra Bayar about when you give a paragraph and they give a prompt TLDR, it will automatically summarize, right? Some people call it emerging ability. Some people would call it, okay, it has seen in training data, so it's kind of obvious, right? But again, so there are certain aspects of these models. For example, they can do new tasks just because you give some examples on how to do them in form of a prompt, and they're able to do it. Whether they have seen it in the pre-training data or not is again something I will leave it as open. Right? And we also see some of these things loosely coming up in the speech models. For example, a loose version of this thing is we have a self-supervised version of a speech model that is trained completely in a self-supervised fashion, like wave-to-wake, where the model is trained to, for example, predict a masked region of a speech or a quantized version of a masked part of a speech. Right? It is not specifically trained for recognition or speech recognition or speaker ID. And then people thought, okay, let's see what these models can do. And they take this pre-trained model, put only a classification head on top, train only that for a specific task, like speaker ID or ASR or translation. And this kind of led to some interest in building superb style evaluation or benchmarks to see if the self-supervised models can actually do these tasks, right? And in parallel, we've also seen, for example, Whisper model, although primarily trained for speech recognition, people have found that since it was trained on lots of data, it can also do some kind of acoustic scene understanding without much fine-tuning. So loosely speaking, maybe this kind of an emerging ability, or maybe it has just seen in pre-training data, that's why it has this ability. But these are what I mean by foundation models and what roughly they are capable of. But there are some limitations of these. For example, they are usually trained on independent of each other. So large language model is trained on text, so it doesn't know how a speech signal looks like, although it might know some general knowledge about what is a speech or how a dog sounds, like what is a dog barking called. But it doesn't actually know the exact information about speech or any signal because it just doesn't have it in its architecture, right? And same goes with the speech models. They don't know anything about generating code, or they don't know how tables look like. Right? Again, same thing applies for many image and other modalities. So ideally, if you want to have some multimodal foundation model, you need to either train them from scratch jointly. Again, it's expensive. It might be difficult to optimize because you need to balance training data. You have a lot of text data. Maybe you need to balance it with a lot of speech data, audio data, or multimodal data, right? So this is kind of difficult. But again, there are many unimodal foundation models out there. Why can't we use them and then somehow connect them or align them in a way that the resulting model can do some multimodal tasks? Right? So this is what I mean by aligning foundation models. How can we make best use of existing unimodal models? They can be generic models or they can be specifically trained for a particular task. But then we want to somehow connect them, interface them in a way that we will avoid some errors or bypass the errors that come through a cascaded pipeline. Right? I will show some examples what I mean by that. But ideally, we were aiming for something that is better than a cascade system. So in the cascades, I have, again, a simple block diagram here. For example, you have a input speech signal, and there is a speech foundation model. For example, it can be a speech recognition system, right? And then it will just transcribe what is in the speech. And then you can take the output and then give an instruction to LLM saying, OK, translate this one to a different language or summarize the transcript. And then you get output. This is the typical cascade system. When I say aligned system, what we have is we take speech foundation model, can be an ASR model, take the hidden representations, either from the output layer or from the middle layer, pass it through yet another neural network, and then, sorry.
Santosh, why do you call upper one cascaded and lower one not? It's also a cascade, right? Except it's a cascade of three modules.
Yes, so OK. At least the difference here, in the upper one, the cascaded implies that we are making a discrete decision on, for example, decoding the speech into a transcript.
So maybe it's just a question of terminology, yeah?
Yes.
Okay.
So it can be, for example, a standalone system, and the other one is a standalone system. And in the bottom part, we, for example, we take hidden representations from the first model, pass it through yet another neural network in a way that the output of the alignment module here is compatible with the subsequent model, in this case, large language model. And again, ideally, the speech model and these large language models, they are quite big, so we do not want to fine-tune them. We want to keep them frozen, just as in the cascades.
May I still, did you ever think about totally parallel system where you would run speech in parallel with the language somehow, or?
So you mean speech foundation and another speech model in parallel, multiple speech models in parallel, or?
Well, you know, so then now you go from speech into language, right? But in my head, I'm recognizing speech, but I also have a prior in form of the language. And I'm convinced, well, actually, you can show that they are combining in parallel.
Yes.
I don't know how to do it, but I mean, I'm just
yes,
wondering.
I agree. So there are some works which are kind of joint speech-text representation models where they take both speech and the text via some pre-processing. They actually go into the same modality, and the same model is expected to process both of them. So there are such works. But in my case, I have slightly simpler one where I assume the first one can do only speech, second one can do only language. Okay. And coming back to this one, ideally we want to train only this part and do not train these two, just to be reflecting the same setup that we have in the cascade scenario, right? Okay, so given this background, I will talk about two applications. So with our experience with two applications, and I will try to share my findings. So the first one is speech-to-text translation.
I want to show you something simple and basic.
So there's a speech sample. Says, I'm going to show you something simple and basic, and we want to translate the speech directly into.
Okay. In the previous slide, what type of alignment model do you use? Like, what do you mean by alignment model?
What I mean by alignment model?
Yeah. What type of architecture or model are you using?
I will come to that.
Oh, okay. Sorry.
So this alignment module can be very specific to each application. Again, I will explain a few different architectures that we have experimented with. So you'll see that. Okay. So the first task is pretty straight, well defined. So you have a speech, and then you want to translate it to text in a target language.
I want to show you something simple and basic.
This is the example. So in a typical cascaded system, what we have is an ASR system. In this case, I'm assuming my ASR is based on encoder-decoder architecture, right? So you have a speech signal in English, you have an ASR which is encoder-decoder based, and then you get some text hypothesis that's also in English. Potentially, there might be some kind of ASR errors, we don't know. And this goes through some kind of punctuation restoration module. Again, this is subject to how this ASR is trained. If I have ASR trained on lowercase text, which was being done until a few years ago, you will have a text that has no punctuation and no true casing. So essentially, you will need some kind of punctuation restoration model that capitalizes starting of the word and nouns, and also puts punctuation. Why is this important? Because machine translation systems are usually trained on text that have true casing and punctuation. So in order to use them in a cascaded setup, you need to have a cascade of 3. But nowadays, we have ASR systems like Whisper that can directly do transcription along with punctuation. So in that case, we don't need this part. But in our experiments, we had this kind of setup. Okay, depending on what this machine translation model is, either we give an instruction or we don't give an instruction. Let's say if this is a specialized model that can just translate from English to Portuguese, we don't need any instruction. For example, if this is a model like T5, which can do multiple tasks, you need some instruction, right? And now, let's come to the alignment architecture. The first one is you have a speech encoder. Again, this is from the ASR part. You have encoder and decoder. We will just take the encoder, put it through some connector. Again, I'm using the word connector and alignment interchangeably, but they both mean same thing in this case. And then, so what I have from speech signal is some speech representations. Maybe I shouldn't call it embedding space, but let's say some kind of hidden representations that are output of a speech encoder. They go through the connector, and note that this speech signal is in seconds. Let's say you have 16 kilohertz. Depending on how this speech encoder process, you have different frame rate here. You might have 40 hertz signal, right? You have like 40 frames per second. And then we have some connector module that possibly downsamples them to reduces the frame rate, maybe 10 hertz, so 10 frames per second. And then this thing goes to the input machine translation encoder, right? And again, here, in this case, the job of the connector when we train it is to take the speech representations, which potentially contain information or lexical information about the content of the speech, and transform them to the input embedding space of the machine translation model. And we know that this model, the input embedding space, is in English. So we are essentially going from some space that is potentially in English in some sense into yet another space that is also in English. The only common thing here is the language. Other than that, the representations might live in a totally different manifold. The speech might contain additional information about the speaker or other things. So the job of the connector here is to retain mostly the linguistic information and put it in the same space as here. Right? So this architecture, I'm calling it as encoder, connector, encoder, decoder, right? So ECED. So we can have slightly different version of it. Again, the first part is the same. We have speech encoder, connector, and then now I can take the output of the connector and maybe connect it directly to the machine translation decoder. And now the machine translation here, if it is from English to Portuguese, the decoder is able to generate Portuguese text, right? So in this case, these representations should somehow align, should somehow live in the embedding space of the Portuguese language, right? So in this case, the connector also has additional job of doing some kind of translating, because for example, the sentence ordering in English may not be same as in Portuguese. So you might have to rearrange the representations. There is no monotonic alignment, monotonic guarantee between these two representations. So in this case, the connector has slightly difficult job, hopefully, to actually also learn this rearrangement of representations so as to be compatible with the target language. Again, this architecture is called encoder, connector, decoder. And now let's get into the details of what should be in the connector, right? So the first one is called Conformer. So it is based on BLIP2, which is from image and text model. So what the Conformer, the original Conformer, what it does is they have a pre-trained image encoder and a large language model, and they want to summarize the image into a fixed number of vectors, and these will go as input to the large language model, and the model will caption the image, right? This was the purpose of Conformer. So it has some fixed number of queries. Let's say you decide beforehand, okay, I will have 64 queries. So everything that is in the speech should somehow be represented in this 64 number of queries. And the speech embedding, which I get from the speech encoder, goes via cross attention. So these are queries, and this is the cross attention. And I have some transformer layers, right? And then I get the same number of outputs, for example, 64 queries, go through some fully connected layer, and we have the final transformed representations. So only this module is trained for the final objective. Again, you have speech encoder, some connector, some decoder, and you have the target. So I can have Conformer in place of this, and then I train only this one for the final objective, right? Again, the Conformer is kind of similar in philosophy with perceiver-based attractors, if you know it from the speaker ID and diarization papers. The second architecture is similar to it, but except there is one main difference. So we have, again, the speech input embeddings. Now here they go to a two-layer convolution neural network, which will, in addition to transforming the embeddings, will also subsample them, right? So again, we can decide how much it has to subsample, maybe 4 times, right? In our case, we did few experiments, and typically we subsample it 4 times. The main difference here is no matter how long your input speech is, the Conformer is trained to summarize it into fixed number of queries. If you have a 1-second sample and you decide Conformer has 64 queries, you have to summarize 1-second speech or the frames here into 64 queries. Whereas on the right side, it is kind of dynamically decided based on the length of the input speech or length of the speech frames that you get from speech encoder. Apart from that, everything else is same. We have same number of transformer layers, same architecture and stuff. Okay, so given this setup, we did some experiments on speech-to-text translation. So the data set is how-to, which is basically some kind of instructional videos on how to fix a puncture in your tire, or how to fix the derailleur in your bike, or how to grow a coriander plant in the garden. So there are different topics, and we have about 200 hours, 270 hours of training data. This is what is used to train the connector module. And then with evaluation, we compute word error rate. For example, if you have some ASR system as a pre-trained speech foundation model or pre-trained speech model, and then the translation is evaluated with BLEU score. So before we go, we will have some baseline systems just to see where we are on this data set, right? The first one is we have to have a speech foundation model. I'm calling it foundation model, but it's just a simple ASR model, right? So this is speech ASR model. Again, we have 3 different architectures. The first two are encoder, all 3 are encoder-decoder based. The first 2 are based on E-branch former encoder, slightly smaller number of parameters, higher number of parameters, and a whisper. And this is yet another baseline that is from ESPnet, just to make sure that we have reasonable speech encoders. So the first one has 38 million parameters and has word error rate of 12. Second one, slightly bigger model, has lower word error rate. Whisper has much lower word error rate. But again, these are, okay. And then we also want to benchmark machine translation models. So the first one is some trained based on Mariana-MT toolkits. It's a completely different toolkit, and it is trained on the how-to data. So it is in domain. So it's kind of the perfect machine translation system that you can build on this data. So it has pretty high BLEU score, and despite being quite small, because it is in domain and well suited. Then we have some T5-based model that we took already from Hugging Face, which was fine-tuned on English to Portuguese, but on different kind of data. So this one was trained on news documents and probably some kind of mainly textual data. So it has lower BLEU score. One of the reasons is the how-to data is speech-based. So the translations or the text forms are slightly formatted in a different way than written text, right? And this is one of the reasons why text-based machine translation model didn't give as good results as the first one, because this one is directly trained on the domain. So there is some kind of domain mismatch here that is causing this difference in our baseline systems. Right. And then we have 2 other baseline. One is end-to-end, where we take speech encoder, machine translation model, connect them, fine-tune everything, right? That is this one, end-to-end, where we initialize with ASR and machine translation and fine-tune everything on the data. So this is kind of ideal system where we have, for example, 45 BLEU score. And the second one is Cascade, where we have the ASR from one of these, followed by TC, which is the punctuation restoration model, and followed by the best machine translation model. And we have 40. So the drop in performance of 17 BLEU score or 16.6 BLEU is due to ASR errors and also due to some errors that might have caused by the punctuation restoration model. And as a reference, we have some implementation of end-to-end from ESPnet, which also is very close to our end-to-end, so that we know that we have reasonably working modules. Now let's go to the experiments where we train only the connector. And we will again play with different types of speech encoders, different types of machine translation models, and different types of connectors. So the first setup is I have a small E-branch former speech encoder. Machine translation is from Mariana-MT, which is the best one. And I have 2 connectors, Q-former and subsampler based. And again, we have two different architectures. If you remember, ECD is encoder, connector, decoder. ECED is encoder, connector, machine translation, encoder, and connector. So in here, again, in all experiments, only the connector is trained. Everything is frozen. So the first one is maybe the ECD architecture. Again, this Conformer and convolution-based one has slightly similar number of transformer layers, but it has slightly higher parameters because of the convolution layer, right? And this is the resulting blue scores. Again, just for the sake of discussion, for this talk, if you see a blue score that is about one blue point different, then you can consider it is reasonably good, and anything less than one blue score is kind of not significant. So we are looking at scores that are at least one blue points on improvement. Right, again, this is also, we have a cascaded system for reference. So from here, at least one message that we can get is we are doing better than the cascade, right? All two different architectures, different types of connectors, all of them are definitely better than the cascade. But maybe some of them are not as good as fully end-to-end, where I fine-tune both the encoder and the decoder, right? So we are still not here yet, but we are pretty close. And now let's go for a slightly bigger table where we change one at a time and see how things change. So the first one, I have different speech encoders, better speech and medium and small, and here different machine translation. Again, if machine translation encoder is not there, this is the ECD architecture, right? And these are the trainable parameters, and this is the type of connector. In the bottom, we have the baselines, right? We always want to be better than the cascade. Ideally, we should be better than the end-to-end. So there is one scenario where we have better numbers here, 47.5, which is more than 2 blue points in this case, right? And here again, we have, maybe because we have better machine translation model, right? Let's now change the connector. We have the same setup. And we can see from the Conformer to subsampler, all the numbers have improved. At least this one has improved by 1 blue point. But if you remember from my earlier baseline, the T5-based system has actually much worse blue score. It had 30, right? The T5 has 38.8, or let's say 39 blue points. So the T5, which is pre-trained on lots of data, but fine-tuned on English to Portuguese text-based machine translation, was not good on how-to data, potentially because of the domain mismatch. But in this case, we are keeping it frozen. Just by training the connector, we are able to actually get better numbers with T5 than the Marian MT, which is trained on how-to, right? So this is the ideal machine translation model. This has a domain mismatch. Again, our hypothesis is that T5 model is actually pretty good in generating text, both spoken style text and written style text. It just have to be slightly calibrated. Calibration is not the right word, but slightly changed in a way that you can enable or activate these abilities in the model. So by training the connector, you can think of connector as some kind of prefix tuning. So if you know LLMs and prefix tuning, where prefix tuning is basically you learn prefix embeddings and keep LLM frozen, and you learn the prefix embeddings for a specific task. And by learning only the prefix embeddings, you are kind of adapting the model or finding some kind of soft prompts that is enabling the model to do a particular task much better. So this is essentially what is happening even here, right? The connector is kind of acting as a prefix tokens that is conditioning the T5 to actually do the translations better. And then we can also say same with if I use full T5 with encoder-decoder architecture. Again, one more message here is whether the connector is directly going from English language space, from speech to English embedding space, or whether going from English to the Portuguese embedding space. Right? So it can kind of do both of them. And now finally, what happens if we put even a better ASR encoder like Whisper, right? We have far more, let's say, better numbers in terms of BLEU scores. Right, and now maybe let's dig a little bit deep into which of these connectors are actually suitable for speech, right? So these are, again, some kind of experiments that tell us a little bit more other than rough BLEU scores over the data set. So what we have here is on x-axis, our test data split into bins of based on speech duration. The first is between 0 to 5 seconds, 5 to 10 seconds, 10 to 15 seconds, and 15 to 20 seconds. And we have different connectors. These are Conformer with different number of queries, and this is the subsampler one. And then we are just computing average BLEU score in each of these buckets, right? So what we want to see is whether you can summarize the entire speech into a fixed number of queries, or do we need to have a variable number of representations or variable number of queries? Right? So what we can see is if we increase the number of queries, the BLEU score improves, but there is a point where you have diminishing returns, right? So this color, which is greenish brown, has 128 queries, more number of queries, but actually has lower BLEU score. If you look at here, this is almost one BLEU score less than the one that has 100 queries. So just by increasing the number of queries, you're not going to get a better capabilities. Again, this is not exhaustive experiments because we just did it on speech translation and that too on one data set. So we have to look at these results only as some kind of limited window into what these things can do. So if you have any questions until this part, I can take.
Yes. Santosh, only one question, because the first architecture that you presented, would you say that you can reuse this connector or adapter for any other translation, like from English to Spanish, for instance?
No. So what I found is the connector is kind of task specific. If you fine tune it for one task, then it can only do that thing.
Yeah, but in the first architecture that you presented, you kind of you transformed the speech input into some
in here.
Then
yes. Okay. So we did some experiments, although I don't have this in here. So they are in the thesis of Shimon. So it depends on how this connector is trained. Right? If I'm training it using a task-specific objective, then this kind of overfits for the task. We can also train it in a kind of non-task specific, for example, using some knowledge distillation, where we take the input embedding space, take this output representations, and try to reduce, for example, mean squared error, or reduce cosine distance between them, right? This is kind of non-task specific because you're trying to map from one manifold to the other manifold. So we also did this. And it works to some extent, but doesn't really give you high performance as when you want to have task-specific objective. So this is kind of limitation of this, and also potentially because these are trained on billions of data, with limited amount of data like 270 hours, you cannot actually learn the exact patterns that are in the embedding space from this one, right? So it's kind of much harder task because you're going from one space where you have sequence of representations and you want to map it to another sequence of representations. So you need to learn what this model actually learned, right? So you need probably potentially much more data, yes.
Okay, thank you.
So yes. So after that, Hinek also has a question.
So I had a more fundamental question on the queries. So do you add some sort of positional embeddings to the queries here?
No. So these queries do not have positional embeddings because the transformer is bidirectional. I think we don't have.
So if you don't, then if the speech has, let's say, the same word being uttered twice or thrice, and then if there are no positional embeddings, does the model still understand?
So even here, they don't have positional encodings on the other side.
Okay. And the second question is, did you do some sort of analysis on what those queries kind of encode within themselves?
No. No, but I assume what they would kind of represent is kind of dominant topics and patterns that are in your training data.
Okay. So because like in some experiments, we have found that most of the time it tries to cheat and like go with some simple patterns, maybe even positional embedding. So.
Hinek also.
Sorry.
Yeah, I also have a question about the connector. I didn't understand. You said that you simply train the connector to solve the task, or do you add any regularization term in the embedding space that is output of the connector?
You mean initialization of the connector?
No, I mean like for training it, you just try to solve the task. I mean your loss function is only in the task. You don't apply any regularization term or something in the embedding space, right?
No, at least in the slides, I don't have those experiments. We also did two-stage training, where first we try to do some knowledge distillation by reducing the mean squared error between these representations and these representations, and then further fine-tune.
Okay.
But we always found that the single stage, both of them actually converge to same performance.
Okay, okay. Have you, sorry.
We also did some experiments in low resource setup, assuming what happens if you have less amount of data for the final task, but lots of data for this one, for self-supervised training. So in that cases, then it kind of helps. Some kind of knowledge distillation-based training where you align the representations as a mean square error, and then little amount of data for the final task.
Okay. Have you made any analysis on how this embedding space looks like?
Okay. So the short answer is no.
Okay.
We didn't made any analysis on what this embedding space looks like. But it is some interesting direction that we were considering for some time to actually see if we can find some kind of mapping. Yeah.
Okay, great. Thank you.
Hinek.
You want to hear another stupid question, right? I mean, this will be extremely stupid. So in this case, you had an instruction was translate to Portuguese, right?
Yes.
How about if you just say translation improve the transcription? Meaning like that you use the language model for fixing the errors from the encoder?
Yes. So, okay, this is what you were saying.
Right.
So with the current LLMs, I think this is how people do. It can work. It can, you can say, improve the transcription.
Right. So
or recognize
how would it work?
In terms of performance, I do not have numbers, but I know that there are people who
do it. It's, it's not as stupid as I thought.
No.
Okay, good.
And for this, we have this specific instruction because in case we have T5 model as this, it was pre-trained with this instruction in mind. We had to use the same one.
Okay, yeah.
That's it. But otherwise, people do.
Okay. So maybe I will reinvent few things in the process. Thank you.
Okay, so this is about our experience with speech-to-text translation. So I will, again, with the same philosophy of connecting models, we will go for a different application. And here I will explain what is the task and what we did and what we found and what are the good results for bad reasons, as Ondra Bayar said. Okay, so dialogue state tracking. So in this, we are interested in task-oriented dialogue, and I have an example to explain what the task, what it means is. So it is basically a conversation between user and agent. A user has a goal in mind, and agent will help achieve that goal. For example, booking a taxi and also booking a restaurant or booking a hotel, right? So these are task-specific dialogues. So here is an example. User says, I'm looking for a hotel to stay that is cheap. And then audience, okay, do you have a specific area you want to stay? So for this turn, so again, when I say turn, maybe in this case it's both user and agent. The state of the dialogue is the domain is hotel, because this is what the user wanted. The slots are price range, cheap, type is hotel. So the structure here that you see is kind of predefined. So it is already known. You already know which domains you have, and for each domain, you know what are the slot names. So all you need to do is, for every turn, identify the correct domain, identify which slot is mentioned, and what is the value. Right? This is dialogue state tracking. And the dialogue can proceed. So you have second turn, and then user will say, I just need to make sure it's cheap, and I need parking. And in this case, we add one more key value pair, parking, yes. And then user will say, yes, I also need a taxi from the train station to the hotel, right? And then the agent says, okay, the name of the hotel is MO, what time would you like the taxi? So in here, the user did not say the hotel name, right? But for the dialogue state tracking, we need to know the domain is also taxi, departure is central train station, and destination is AMO. So there is some kind of co-reference resolution that the model has to solve, right? So in dialogue state tracking, this is one of the main challenges that you need to kind of solve what is the actual entity that the user is referring. Sometimes the user might, at the end of dialogue, change mind and say, okay, I will cancel the hotel, but just keep the taxi. So in the final dialogue for the turn, we should not have the domain hotel and all of this. This should be empty, and we should only have this information, right? Again, this is done for every turn, and at every turn, we have to get everything correctly so that the dialogue can proceed. And one more thing that we don't do in this is generating responses, right? So this task is only a subpart in the whole dialogue system. We only want to track the status of the dialogue. We do not want to generate responses. So what we do is instead, we will already use existing responses that are in the conversation, and then the dialogue just flows. So it's a fixed dialogue. The goal is to identify the dialogue state as accurately as possible. So how is it evaluated is slot error rate and joint goal accuracy. The slot error rate is same as in worded rate, so you can make for every slot that is mentioned, the model can correctly recognize it or completely ignore it, right? That's a deletion, or misunderstand what it is, price range instead of cheap, it can say expensive, right? So that's the substitution. And insertion is when it hallucinates additional slot name value that is not mentioned in here. For example, it can say Wi-Fi, yes, right? Although it was not mentioned, the model predicts Wi-Fi yes, then it's also an error. So that is the slot error rate. The second metric is joint goal accuracy. What it means is in every turn, like for this turn, this is the, so for the first turn, this is the ground truth, domain, and slot values. If the model is able to predict everything correctly, which means perfectly this domain name and perfectly both the slot values, then you get one hit. If it makes even a single mistake, it's a miss, right? So you have a corpus of, let's say, 1,000 dialogues. Each dialogue has 10 turns, so eventually you have 10,000 turns. And out of these 10,000 turns, how many times the model has perfectly identified the dialogue state? That is joint goal accuracy, right? The percentage of turns in which the model has perfectly predicted everything. Okay, so these are two evaluation metrics that are, sorry. Yes, this slot, so for slots there is two, name and a value. The slot names are fixed. The slot names are fixed, but values can change because if it is hotel name, it's kind of open-ended.
Yeah, what I want to know is like, are the slots fixed per each domain beforehand? Okay.
Yes, yes. The structure of it is predefined, and that's why this is called task-oriented. Okay, so now let's see how we actually approach this problem. So what we have here is now two-stage training, and I will come to that why we have two-stage training. Again, the scheme is the first scheme is similar as before. We have some speech foundation model, can be a speech encoder from an ASR, some connector or alignment module, some LLM, followed by some that takes some instruction, right? And then it gives us the ASR hypothesis. I think this is something similar to what you were asking. Yeah. And the second scheme is where we also, let's say, fine-tune the speech encoder, right? So again, stage one is only ASR pre-training, and stage two is when we want to do dialogue state tracking, right? So you have user utterance in turn one, it goes to this speech encoder, goes to the alignment module, you have LLM, and then it predicts the ASR hypothesis, followed by the current state of the dialogue. And then whatever is the hypothesis becomes dialogue history, and then we have second user turn. Right? And in this case, I have example where I only have user turns, I do not have agent turns, but we did experiments in both scenarios where the model will attend only to user turns, and some experiments where model will attend to both user and agent turns. The reason is most of the information is typically present in user dialogues because this is the user's intent that we are looking for. But sometimes the agent can also suggest something, suggest the hotel name or something. So the agent turns also have some information. But there's a disadvantage or kind of limitation because if we put both user, agent, and user utterance and agent utterance, the dialogue history will actually become longer and longer, right? If you have very long dialogue, and if you keep concatenating user and agent utterances, you have much longer context, and some of the LLMs are not trained to parse such a long context. Right? If you have a very good LLM that takes very long context, then there's no problem. But if you're dealing with slightly smaller LLMs that have less receptive field, then they don't fit in. Again, we want to see what is the trade-off when we make this. So in stage 2 training, we have setup, and we also have some experiments where we, let's say, fine-tune part of the LLM, for example, by introducing low-rank adapters, right? And once these low-rank adapters are fine-tuned for the task, it can actually enable LLM to do the task better, but at the expense of the LLM not being able to do any other thing, right? So how this whole thing is done, maybe in simple text, is there is some instruction, very, very simple text. We have sequence of speech embeddings that come out of the alignment module. And then there is the dialogue history, says user. So for turn 1, there is no dialogue history. It's actually empty. And let's say there is some dialogue history, and then current turn is what the ASR has predicted. This is the ASR hypothesis, followed by domain. So we formulate the whole output into a sequence of text, but formatted in a JSON style so that we can easily extract what is the ASR hypothesis, what are the domains, what are slots, so that we can evaluate. And nowadays, LLMs are trained on lots of code, so they can actually generate pretty good JSON structure, and they know how to close the brackets, how to open them, and things like that. So this is something quite easy for current LLMs to do. So we take advantage of this ability of the LLMs and formulate our task in this fashion. Okay, so go to the data set. The first data set is spoken was. These are enacted conversations. Maybe I'll play an example. And okay.
Hello, can you hear me?
Yes, sure. Customer Service Center, how can I help you?
Hi, I'm now traveling in Cambridge. I think I'm in downtown area. I want to eat some Indian food. Can you find a moderate restaurant for me?
Okay, I understand. You are in the center of the city and you are looking for some Indian food in a moderate price range.
Yes, that is correct.
Okay, I'll find one for you. I'm sorry, there's no Indian food that meets your requirement. How about some Turkish food?
Oh, that's a little bit, okay. Then I accept the Turkish food. Can I have the address and postcode of the restaurant?
Okay. The restaurant that I found for you is Anatolia, and the address is 30 Bridge.
Okay, so this is how the conversation is. It's kind of enacted, but you can already see that in the beginning, the user wanted to look for an Indian restaurant, and then later the agent said, okay, there are no restaurants available or something like that. So for the beginning part of the dialogue state, the model has to correctly predict domain restaurant, cuisine Indian, but later it has to remove that. It has to correct it. So this data set is probably one of the difficult and open spoken data sets that is based on speech. It covers multiple domains. So there's hotel, taxi, restaurant, and in one dialogue, user can talk about two things. And it is also potentially difficult. At least this was released in 2023. And these were the different baselines that they had back then. And this was also ChatGPT released in 2022 November, so they also evaluated how good ChatGPT is back then, right? And this is the joint goal accuracy, which means the number of turns or the percentage of turns in which the model has predicted everything, the domains and slots perfectly. So there are a bunch of cascade systems, which is the ASR from the Alibaba API, followed by text-based dialogue state tracking. So all, I think the first one is Cascade, second one is Cascade, the third one is kind of similar to what we are doing, kind of connecting speech encoder with dialogue state tracking model, but everything is kind of fine-tuned. So VAVLM is a speech encoder here. This is again a Cascade. I believe this is also the model that very similar to what we are intend to do. Again, so there are two things here. One is the data set is kind of hard at that point of time, right? And it also has a lot of these co-reference resolutions that the model has to solve. The second data set is speech-aware multi-voice. This is actually not a speech data set. This is text-based data set that was already existed. And then what they did is they took the written conversations and they asked people to read them or try to rephrase them. So it is not fully realistic, but this is what we have. The only difference that the speech version of this data set is usually all the dialogues are based on the restaurant names, hotel names, and everything is based on Cambridge in UK. And what they did is, for this part, they changed the development and test set and made them based on New York, USA. So this is a kind of domain shift between the training and dev, right? And this is what makes this one interesting from this point of view. And the effect of this domain mismatch is, for example, in the original development set, where you have everything based on Cambridge, the training data also has names and entities based on Cambridge. And the new dev set, it has everything based on New York, right? If the models are able to really extract names of restaurants, the correct mention of times for booking a taxi or place names, they shouldn't have so much of a difference. But if the models were memorizing these things, then when you change it, you might have this drop. Right? This is what actually inspired them to create a challenge in dialogue state tracking. So DSTC is a dialogue system technology challenge that happens every year or sometimes once in 2 years. And in 2023, this was one of the tracks in this challenge that was proposed by folks from Google. Okay, so this is what makes this second data set unique and interesting. Okay, so I will quickly jump to results. There are numbers, but we only need to look at some of them. So don't be afraid. I will highlight which ones to look. Rest you can ignore. So the first one is, in the orange, what we have is a cascade system. So we run ASR, followed by Olmo 1 billion language model that is fine-tuned for dialogue state tracking, right? It is fully fine-tuned. The first two is using the original transcripts that came with the data set that had about, I believe, 18 or 20% word error rate. And the second one is the one with whisper transcript, which has about 5% or between 5 to 6% word error rate. So the actual data set doesn't have ground truth transcriptions. So we manually corrected a subset of transcriptions to estimate the word error rates. Again, so having lower word error rate kind of improves joint goal accuracy by about 2 to 3% and reduces slot error rate by about 4%. Right? This is the effect of word error rate. Everything else remains same. And okay, maybe we can also look, before looking into the green one, let's also look into multi-voice scores. So here, these are much lower than this. Again, potentially because of the problem I've said. The training data is based on Cambridge. All the entity names, restaurant names are in Cambridge, whereas the dev and test set have entities and restaurants based in New York. And this is where most of the errors are coming. So, and the second set of experiments that I want you to look is here. So we now combine both the training data, right? Both spoken voice and multi-voice. And then either we fully fine-tune the Olmo language model for the task, or we only fine-tune part of the parameters using low-rank adapters. So we can see a slight drop in performance. But if I look at here, this one has slightly better performance than this. So again, the hypothesis here is that when we are fully fine-tuning the model on this data, the LLM is kind of memorizing all the entities that are based in Cambridge and is actually having slightly worse performance on multivos because it has entities from New York. But nevertheless, 27.72 is the number that we get if we train only on one data set, right? Okay, and the third one that we should potentially see here is these two blue numbers. The only difference here is whether we use both user and agent dialogues in the training and inference or use only user dialogues, right? So the first part of table, we use only user utterances. So we are trying to get the dialogue state only from user dialogues, only user turns, whereas in here we have both user and agent. So we know that agent also sometimes mentions some information that should go into the dialogue state. For example, agent can suggest a restaurant name that the user will say yes, right? So this is the effect of what happens if we exclude agent turns from the dialogue. Okay, and when we were looking at errors, we found that a lot of errors are coming due to the way it is evaluated and the way the LLM outputs. For example, user says, I'm looking for I would like a reservation in the Grand Hotel, right? The ground truth says the Grand Hotel, but model predicts the hotel name as just Grand Hotel. Is it correct or wrong? I mean, ideally, it's the right thing, right? Both are same. So what we did is we did some fuzzy matching where we assume we have all the list of hotels, all the list of restaurants, all the list of train stations, city names, and then whatever model predicts, we try to find the best match from our list of database. And we say, okay, this is the one, right? This is the fuzzy matching. And now we will see what happens if we do this fuzzy matching in connection with some more experiments. Right. So in here now we are already jumping to the aligned experiments where my speech encoder is VAVLM. So VAVLM is a speech model that is trained in self-supervised fashion. So it cannot do any ASR or translation or anything. And this is also one of the reasons why we needed two-stage training, where the first stage is to get the ASR transcripts out of VAVLM using the connector. So in our case, we have connector is again subsampler-based, LLM is Olmo 1 billion. And one of the reasons why we we used Olmo is because we know what is its training data. So the complete training data of Olmo language model is open, along with the training scripts and intermediate checkpoints. So we can always look back whether my test data has been contaminated or not, right? So we want to see how the models will perform if we have fully open foundation models. So VAVLM is also trained on LibreSpeech, 60 hours of LibreSpeech and 24,000 hours of, I think, Vox Populi or one of other corpus. So we know what VAVLM has been trained on. So this is some experiments where we want to have fully open models. And okay, so in here, maybe the important results is the, let's say, the difference between these two. If I have the fuzzy matching of the entities, then we get about 2% improvement. And other than that, the other interesting part here is this one. What happens if I train only the connector, as in the speech translation experiments we did, right? We get only 20 blue score, but once we fine-tune also the LLM with some low-rank adapters, the performance suddenly improves drastically. Again, one of the reasons is Olmo 1 billion model by itself is trained only on next token prediction. It hasn't gone through any instruction tuning or task-specific tuning. So it doesn't have the ability to do dialog state tracking. And it is one of the reasons why it requires some adapter-based fine-tuning to actually give this ability. So the second part is when we train on both spoken voice and multi-voice. And when you see the numbers on this side are lower than this one, again, potentially because of this domain mismatch reason. Again, we have, a bunch of experiments, maybe one. So what here we did is we have a 3-stage training where we jointly train for spoken voice and multi-voice, and then do one single epoch on each data set, right? This is what this means. So we have LoRA adapters for large language model. We use both user and agent, and then we do one epoch fine-tuning on spoken voice, right? This is this number. And then we take the same model, fine-tune for one epoch on multi-voice, right? So this gives actually slightly almost 1% improvement in joint goal accuracy, kind of suggests that these models are very quick in memorizing things, and you always need to somehow balance it. Again, we do not have any perfect way to avoid it, but this is one of the problems that we have noticed. So the best model on multi-voice is when you train only on multi-voice and do not see any of the spoken voice data, right? This one gives us like 21.6, despite being the dev set being difficult for the domain mismatch reasons. Okay, so the summary of main results, it also has some new numbers. So the first two are from the 2023, the best numbers. 2 years later, even a simple cascade system with off-the-shelf Whisper and almost 1 billion outperforms the bigger systems from 2 years ago, right? Again, the number 4 is the fully open model, where speech models and large language models are fully open, and this is the best number that we get, 34. The final one is we just replaced the LLM with the Gamma 2 9 billion model, which was instruction tuned. We don't know what it was trained on. Maybe there was contamination, maybe there was not. But then we want to see what happens if you take a much bigger model, and then there is a drastic improvement in performance.
There's still a lot of room to improve.
Yes, and we also found some annotation errors. So we need to also fix, or at least know what are the errors that we cannot actually recover. And I will tell you some of the errors. I do not have examples, but I can tell what are the errors that are happening. The main errors that we have seen are mentions of time. So when user says, I would like a taxi at 5:15, and if the word 5:15 is not seen in training data, model is not going to get it correctly in the dev set or test set. So the mentions of time, or these digits, the model is kind of memorizing, partly due to the way they are tokenized. And I think that's one of the main reasons, partly why they are tokenized, and it just memorizes things. One way that we could solve is to take all the numbers and then convert them into a spoken form. Like 5:15 will be 5, FIVV, 5:15. And this is something that we are looking could kind of potentially overcome this kind of an issue. So, sorry, so Hinek.
I don't know why I got the microphone, but since I got it, I may ask. So output from your auditory, from your front end is wave LM parameters.
So
you get the wave LM parameters out of, and then what your connector does.
So okay.
Yeah, maybe this one, alignment module.
Yeah. So this is a WAV-LM model.
Right, and so there is.
And this is there are two convolution layers that will
No, but input and output. So input is clear, but what is output?
The output is also some kind of hidden representations.
I see, and so what does it change? Why do I need it, this alignment module?
Because, for example, so we need to somehow transfer the information, what is spoken in here, to the LLM, right?
Yes.
So in first stage, we do ASR. So the first thing that LLM will do is actually speech recognition.
Yes, but I still have a question about this alignment module. Input is output from WaveLM. What is the output? What is it that you want it to do so that LLM likes it? Because that's the reason for why you have it, because LLM wouldn't like the output from the WaveLM directly, right?
Yes. So ideally, we would like these representations from here to live in the same embedding space as the input embedding space of LLM.
I see.
So the input of embedding space of LLM is some vocabulary of tokens that is specific to a model. For example, for Olmo, we have 50,000 tokens in our vocabulary. Some of them are words, some of them are the special tokens that are in code, and things like that. So we want these representations to be as close as possible to these.
Okay, maybe I need a little bit more.
And again, I do not have a clear answer to say, okay, these representations now match to this word and this word. This is something I do not have to actually clearly answer your question, but this is something that we are lacking in.
Okay, thank you very much, thank you.
So we did some analysis, and what we found is it is usually the LLM that does a lot of the heavy lifting because it memorizes a lot of things. Even if some of the information from speech is transferred, it can actually recollect from its memory and predict what is going to be the output. So it is not necessary that the model has got everything correctly. We believe we also have some word error rate numbers to see if, I think it's probably not for this, it's for different set of experiments.
No, I think it's for this, so the word errors are about 10%.
Okay.
So 5% worse than the whisper.
So
I'll just repeat, the word error rates that we get from the LLMs are about 10%, so 5% worse than the whisper large baseline.
So the word error rate of this particular part is 10%, but for whisper it is 5.9% or something. Again, based on our previous experiments, we found any kind of fine-tuning kind of leads to some forgetting. For example, with the speech translation experiments, when the connector is trained for translate to Portuguese, we cannot just change the instruction and expect the model to translate to something else. But this is fine as long as if you know my target application is fixed, so you can fully fine-tune. And what we also think is important is when we need to do some kind of multitask training. Ideally, the same tasks that the LLM was pre-trained on, so that we retain the same abilities when we are aligning these models. But in practice, this means scaling more data and having more and more compute power. But at the same time, maybe there is a slightly better way on actually doing these tasks. So this is some open kind of question that we are kind of investigating on how can we actually train the alignment module or connector module in a better way, or in a way that at least tells us what's happening, and maybe avoid the problems of memorization or task overfitting. But this is open questions. Okay, that brings me to the end of my talk. So any kind of questions?